All right, welcome. Ever felt like you've hit a wall with the basic differentiation rules? Like you've got the standard tools, but you need more? Well, you're in exactly the right place. Today, we're going to give your calculus toolkit a serious power upgrade.
I mean, think about it. How do we actually measure the rate of change for something like population growth or even radioactive decay? These things don't grow in a straight line. The answer, well, it's all about exponential and logarithmic functions. And to really get a grip on how fast they're changing, we're going to need some pretty special tools.
Look, you've already got the basics in your belt, right? The power rule, product rule, quotient rule. Those are your trusty hammers and screwdrivers. They get the job done for a lot of things. But today we're adding the pro-level gear. We're talking about the power tools that'll let you handle exponentials, logarithms, and functions that look way more complicated.
So, first up in our new collection of power tools, let's call this one the exponential wrench. This is going to be our go-to for anything involving the natural exponential function, and it's all built around that one kind of magical number, e.
Okay, so here's the thing that makes e so cool. The function e to the x. It's its own derivative. I mean, stop and think about that for a second. That is just incredible. It means its rate of change at any point is exactly the same as its value at that point. And that more general formula you see, that's just what happens when you mix this amazing property with the chain rule we already know. It lets us find the derivative of e raised to, well, pretty much any function you can throw at it.
All right, let's actually put this new tool to work. This problem here is a perfect example of how we're going to combine our new gear with the stuff we already know. So, right away you can see it's a fraction. It's a quotient. That means we got to start with the quotient rule. But look closely. When it comes time to differentiate that top part, the numerator, bam! That's where our new exponential rule comes into play. And of course, the chain rule is tagging along for the ride. After that, it's really just a matter of cleaning things up, and boom, we've solved it.
Okay, tool number 1 is in the bag. Next up for our toolkit, the logarithmic key. You know, if exponential functions are all about that super fast growth, then logarithms are kind of their inverse cousins. And figuring out their derivatives, well, that's going to unlock a whole new set of problems for us.
And check this out. This is honestly one of the most beautiful, elegant results in all of calculus. For any positive number x, the derivative of its natural log is just 1 over x. That's it. It's so clean, so simple, but believe me, it is unbelievably powerful. Okay, now take a look at this function. At first glance, taking its derivative looks like it's going to be a real headache, right? But here's the pro move, the secret trick. You can use the properties of logarithms to simplify everything before you even think about differentiating. That messy log of a fraction and a product, we can just break it down into a simple sum and difference of logs. And now differentiating each piece is super easy. This is a classic case of working smarter, not harder. All right, so far we've added a couple of specific tools to our kit, but what we're about to look at now is different. It's not just another rule, it's a master technique, a whole strategy. Think of this as the logarithmic Swiss Army knife of differentiation.
So what do you do when a function gets, well, just plain messy? I'm talking a tangled up combination of products, quotients, square roots, exponents, just a total mess. If you tried to attack this thing with just the product and quotient rules, it would be an absolute nightmare. Seriously.
But don't worry, we have a plan. There's a clear 5-step strategy to deal with exactly this kind of problem. It's called logarithmic differentiation. The core idea is that we take the natural log of both sides, and by doing that, we magically transform that tangled web of multiplication and division into simple, manageable addition and subtraction. It makes the whole thing so much easier to handle.
And here it is. Let's watch this strategy in action. See? We take the natural log, and suddenly we can use those log properties to just expand that nightmare fraction into a nice, simple sum. Then we differentiate. Now, on the left side, we've got ln of y, so we have to use implicit differentiation, which gives us y prime over y. A little bit of algebra to get dy by dx by itself, and for the final step, we just plug the original messy function back in for y. Just like that, the problem that looked impossible is completely dismantled piece by piece. Just take a second and let that sink in. A function that looked almost impossible to differentiate just moments ago is now something you have a clear step-by-step strategy to solve. That's not just a small step up. That is a serious upgrade to your mathematical power.
Okay, our next tool is for a totally different kind of situation. What if you don't actually care about the derivative of a function, but you need the derivative of its inverse? Well, yep, there's a tool for that. We'll call it the inverse function tool.
The inverse function theorem is going to be our guide here. It's a really clever way to kind of work backwards. Basically, it says that the derivative of an inverse function is just 1 over the derivative of the original function, but, and this is the key part, evaluated at the inverse. To put it simply, if you know the slope at a point on some function, this theorem lets you figure out the slope at the matching point on its inverse. Pretty neat, huh?
So let's try it out. Here, instead of differentiating g of x directly, we're going to find its inverse, which is f of x, and differentiate that instead. Then we just plug that result into our theorem's formula. And look at that. The answer we get using this indirect method matches the direct derivative perfectly. It's just another powerful way to tackle a problem from a different angle.
Okay, we're ready for our final toolkit upgrade. This time, we're adding a set of 6 very specialized but absolutely essential tools. These are for when you're dealing with angles, triangles, all that geometry stuff. We're talking about the derivatives of the inverse trig functions.
Now, I know what you're thinking. You look at this list, and at first glance, it seems like a lot to memorize. 6 new formulas, they've all got square roots and fractions, but hang on. Don't let it scare you off, because there are some really helpful patterns hidden in here that make it much easier.
The key is to look for the symmetry. Check out the derivatives for inverse sine and inverse cosine. See that? They're exactly the same, except the cosine one has a negative sign. And this exact same pattern holds true for the other pairs. Tangent and cotangent are a pair, secant and cosecant are a pair. So really, instead of memorizing 6 different formulas, you just have to learn 3 and remember that its cofunction buddy is just the negative version. Way more manageable, right?
All right, let's wrap this up with one last example. We need to find the derivative of the inverse sine of 2x cubed. This is a total classic chain rule problem. First, we apply our brand new inverse sine formula. But instead of just plugging in x, we have to plug in our whole inner function, that 2x cubed. Then you know the drill. We multiply by the derivative of that inner part. A little bit of cleanup, and there it is. We have our answer.
So there you have it, the exponential wrench, the logarithmic key, that awesome Swiss Army knife technique, and a whole set of specialized inverse tools. Your calculus toolkit is officially upgraded. But remember, having the best tools in the world doesn't mean anything if you don't use them. So now the only question left is, what complex, real-world change are you going to measure next?